All right, so we're looking at problem in Chapter 3, problem number 27, which is part of your Chapter 3 homework. And it reads, a ball is thrown horizontally from a 20-meter high building with a speed of 5 meters per second. And there's 4 parts to this problem that's kind of all based on getting the just the idea of what's going on in this problem. And part A says make a sketch of the ball's trajectory. Part B says draw a graph Vx, the horizontal velocity as a function of time, include units on both axes. Part C is draw a graph of Vy, the vertical velocity as a function of time, include units on both axes. And then part D is the actual solving a question, and that's how far from the base of the building does the ball hit the ground. Okay, so I'm going to make a sketch to start this off, and I'm going to first need my building. So I have my building right there, and essentially what's happening is I have a projectile that's starting at the top of the building here, and it's going to get thrown horizontally off the side. So there's going to be some initial velocity directly to the right, and it's going to just follow a projectile path down to the ground. So for me to sketch this, it's just going to go straight down to the ground. All right. And I kind of ran out of space, but that'll be all right. So I'm following a path that starts from the top, it goes straight off, and it follows down to the ground. Perfect. So that is part A. So part B is asking me to draw a graph of the velocity in the x direction, the horizontal velocity as a function of time, including units in both axes. So you notice that here in time, I put it in seconds because we always deal with time in seconds. And on the left-hand side, I have the velocity in meters per second because that's our units for that. Now, the big concept with projectile motion is that the y determines the time in the air, and the acceleration determines the velocity in the y direction. But in the x direction, the velocity is constant. So if I were to sketch this in the x direction, it's just going to be some non-zero constant in the x direction. So I'm just going to put it at right here, and it's a constant velocity. So it's always constant velocity in the x direction. Part C, on the other hand, is looking at the velocity in the y direction. So the velocity in the y direction I had to set up a little bit differently. Now, when you notice here on my picture, this, I'm going to go ahead and call this at the bottom as 0 and the top as positive y. Well, that means that it's speeding up in the negative direction. So when I have my velocity graph, speeding up in the negative direction, but it starts at rest in the y direction. So I'm actually going to start at 0, and it's speeding up in the negative direction. And that makes sense because it's a negative slope, and my acceleration is the slope of a velocity versus time graph. So technically, the slope of this line equals negative 9.8 meters per second squared, or acceleration due to gravity. Let me just see if I can fix that. There we go. So 9.8 meters per second squared, or the acceleration due to gravity. All right, so I went ahead and made those lines pretty obvious just so we can see them. And again, my slope for this graph right here is the acceleration due to gravity. Okay, the last part of this problem we're looking at is how far from the base of the building does the ball hit the ground? And again, the entire concept is the ball is being thrown off this building at 5 meters per second. The building's 20 meters high, and it's going to go some displacement. So I'm going to go ahead and label all my variables. Alright, so those are all the variables. Looking at the top, my initial position in y is 20 meters because that's how tall the building is. My final y is going to be 0 meters because it ends up on ground level. The velocity initial in the y direction is 0 meters per second because it says the ball is thrown horizontally. So because there's not an angle, my initial velocity in the y direction is 0 meters per second. The final velocity in the y direction I do not know, but I know that the ball accelerates in the y direction at negative 9.80 meters per second squared. And then the x direction, which we talked about over here, is completely independent of the y direction, and my velocity in the x direction is 5 meters per second, and that will never ever change. So back to the concept of projectile motion. If I have a ball in the air, what determines the time in the air is going to be the y direction. So I'm starting in the initial y at 0 meters per second at 20 meters, and I'm wondering essentially how long it takes me to go from 20 meters to 0 meters with acceleration at 9.8 meters per second squared. So I have yi, I have yf, I have viy, and I'm looking for t. So I'm going to choose equation number 5 in the form of y's. Okay, so I have my equation right here, and just a reminder that I have yi, it's 20 meters, I have yf, it's 0 meters. My vit actually disappears because vi is 0 meters per second, and I have 1/2 gt squared. And the whole thing I'm solving for is t, so I'm going to go ahead and rearrange my equation for t, with in mind that I can cancel this out, and as well that yf is 0. And if you recall, this equation is actually the special case formula. So whenever I know the maximum height that a projectile reaches, I can solve for the time down using this equation. But in this case, I'm just going to plug it in. So I'm going to use my calculator, and I have t down equals the square root of -2 times my initial height, which is 20 meters, divided by the 9.8 meters per second squared. Okay, so I plugged that into my equation, and I got an answer of t equals 2.02 seconds. That's the time down. But we know that this is just the first part of that problem. What the problem is actually asking me for, and this again is part D, is how far away or how far from the base of the building does the ball hit the ground. So I'm actually looking at the displacement in the x direction, and the displacement in the x direction is undergoing uniform motion. So we have the easiest formula of delta x equals vx times t. So there's my formula. The thing we're solving for is delta x, which is already on the left-hand side, which is great. The time in the air, I just got based on the time in the air in the y direction. So literally all I have to do is I have to take the 5 meters per second, and I need to plug in, so my delta x will equal the 5.0 meters per second times the 2.02 seconds. And if I plug that into my calculator, I get an answer of 10.1 meters. Delta x equals 10.1 meters. So that is my final answer. And again, my displacement in the x direction is dependent on the time which I get from the y direction from the projectile. And this again is a special case formula that I can only use in certain times. Make sure you check the notes to make sure you know when that is. And that is problem 3.27.